Okay, so what we're going to look at today is acyl chlorides, and just carrying on with the organic chemistry topic. So acyl chlorides, they're really, really easy to make, and they're a really good starting point actually for making other types of molecules. First of all, we'll look at what their functional group is. So their functional group is COCl. So acyl or acid chlorides, so they can be called either, have a functional group COCl, and all their names end in oil chloride. They all end in oil chloride. So I'm going to draw you an example of one now, just to show you an example of one. So I'm going to draw you ethanol chloride. So I'm going to draw a functional group on in red, just so you can tell that that's our functional group that we're looking at. And that is ethanol chloride. And another one I'm going to draw for you, and we'll look at naming that one straight away, is I'm going to draw one on here. Now, this molecule is going to have 5 carbons on it. I'm just going to add the functional group on straight away at the end to make it a little bit easier for myself. And then I'll carry on with the rest of the molecule. So this molecule here, I'm going to go through and name it in parts. So first of all, let's look at numbering the carbons. We've got carbon 1, 2, 3, 4, and 5. You can start here from carbon 1, 2, 3, 4, 5, which would make the most sense. So we're going to go here 1, 2, 3, 4, 5. I'm going to look at this hydroxyl group that we've got here in blue, and that's at carbon 4. So this molecule is 4-hydroxy. And we've got a methyl group. So we've got 2 methyl groups at carbons 2 and 3. So that's 2, 3 dimethyl. Oh, not sure why my green pen's so big. 1 second. Dimethyl, 5 carbons, so pentane, it's pent, and oil chloride. So if I make sure I've got this bit in the same color, oil chloride. So 4-hydroxy for that hydroxyl group here, 2, 3 dimethyl, pentan, 5 carbons, oil chloride. So that is how we would name our acyl chlorides. Carbon atoms in this situation, why I've numbered them this way, the carbon atoms are numbered from the end with the acyl function group, exactly the same as what you would do with carboxylic acids. So we always start with this one being our number 1. Acyl chlorides, what's good about them? Well, they really, really easily lose their chlorine. So they can react with a lot of different molecules to lose that chlorine, and that's what we're going to look at now. So one of the molecules they can react with to lose that chlorine, I'm just going to zoom in again actually. Oops. So one of the molecules that they can react with to lose that chlorine is water. So I'm going to use ethanol chloride as our starting acyl chloride, just as this example for every single one where they're reacting. It just makes it a little bit easier. So I'm going to draw that ethanol oil chloride on now. So we've got H3C, and then that is going to bond. I'm going to just draw out the whole functional group. And it can react with water. So I'm going to show it reacting with water. So I'm going to add water on, which obviously is H2O. Now, when the ethanol chloride, and I'm just making sure we've got that labeled on as well. So our ethanol chloride reacts with water. This is a vigorous reaction. So that is really important to remember. It is a vigorous reaction. And it's a vigorous reaction with cold water. So that's quite important that we realize that we're using cold water. And what is produced is a carboxylic acid. So that's what we're going to have a quick look at now. So the ethanol chloride reacts with the water and it produces a carboxylic acid. So what we get is this. OH from our water. So we get ethanoic acid being produced. And then we get some HCl left over at the end. So we get ethanoic acid being produced. So you can see that, I don't know why that says O here, and it won't rub out. That should be a Cl. So let's just make that a C. So that chlorine reacts, it loses that really quickly. It loses that chlorine, it's replaced with the OH group from the water. And then we have hydrochloric acid being formed, HCl over there, and then ethanoic acid is our product here. So acyl chlorides, they react with water really vigorously when it's cold water, and they produce a carboxylic acid. So in this instance, it was ethanoic acid. Not only do they react with water, they also react with alcohols. So again, we're going to draw out ethanol chloride. And it's going to react in this situation. We're going to react it with an alcohol. Now, again, this one is a vigorous reaction and it's at room temperature. So that's really important to remember. It's at room temperature. And what is produced is an ester. So what happens is, we're going to look at that now, is our ethanol chloride. We're going to lose that chlorine again. And what happens when we make this ester is we get methyl ethanoate being formed. So again, we've still got that carbon and the oxygen, that chlorine is lost. And instead of the chlorine being there, we have the OC3H from our alcohol going on. And then that produces for us methyl ethanoate. And then what is left over again is hydrochloric acid. And we've got one hydrogen from our alcohol and the chlorine from the ethanol chloride. And that is a vigorous reaction at room temperature. There's two more things that they react with. So we've got acyl chlorides react really well with water, vigorous, and they produce a carboxylic acid. Alcohols, vigorous at room temperature, and they produce an ester. Another thing they react with is ammonia. So let's have a look at ammonia and how they react with ammonia. So when, again, I'm going to draw ethanol chlorate up again. When ethanol oil chlorate reacts with ammonia, what is produced is a violent reaction, so more reactive than water and alcohols, because this time it's now a violent reaction, and we have an amide being produced, and we'll have a look at what that looks like now. our ethanol chloride here, and this is now a violent reaction at room temp, and we're going to make an amide. So let's add ammonia on. So NH3. And what we get produced is this. We will get ethane amide. We still have that carbon with a double bond oxygen from the ethanol chloride, but this time coming off that carbon from that functional group, we have NH2, which then will make that ethane amide. And as per usual, we're left then with hydrochloric acid, hydrogen from the ammonia, and then the chlorine from the ethanol chloride. And then the other thing we can make, well, the final thing that we can react acyl chlorides with is primary amines. And that is the last one that we'll look at now. So we can react them with primary amines. These, again, are a violent reaction. These are at room temperature. And this time we're making an N-substituted amide. And we'll look into amines and amides in a lot more detail in another session. So don't worry about what they are in too much detail at the minute. All that you need to know is when we react acyl chlorides with ammonia, we make an amide. And when we react acyl chlorides with amines, we make an N-substituted amide. But we'll look into amines and amides in a lot more detail in another session. So don't worry too much. So yeah, so this is a violent reaction. We're going to have that ethanol chloride here again. And we are going to react it with a primary amine. So here is an example of a primary amine. And what we're going to produce is, I'm going to write the name of this one up first, actually. It's N-methyl ethanamide. And that looks like this. Still got that carbon, double bond oxygen, but where the carbon will join to chlorine, we've now got NHCH3, and then you can guess it, hydrochloric acid. Only thing I want to go back over in these, so they're the 4 things acyl chlorides can react with and lose their chlorine really, really easily. So we have water, that's a vigorous reaction in cold water, and we are making a carboxylic acid. So I'm just going to start that here, and we're going to have a carboxylic acid. Alcohols, if we react them with acyl chlorides, we are, again, it's vigorous, it's at room temperature, and we produce an ester. Now, something I want to point out about alcohols is this is a reversible reaction. It's not a reversible reaction. This irreversible reaction is what I'm trying to say. This irreversible reaction is a much easier and a much faster way to produce an ester than esterification. So when we looked at esterification before, when we did the session on esters, if you're not sure, look back at alcohols and esters. It will probably in the alcohols 2 session, but it'll be somewhere in 1 or 2. This is way faster for making an ester than esterification. So actually getting an acyl chloride, removing the chlorine by reacting it with the alcohol at room temperature, we make these esters a lot quicker. So that's a better way of doing that. So when these are happening, when they're losing, these acyl chlorides are losing their chlorine, whether it's with water, with alcohols, with ammonia, or with primary amines, the chlorine is substituted either by, every time this is happening, it's being substituted either by an oxygen So the chlorine is going to be substituted either by oxygen or by a nitrogen group. And what happens when this happens is misty fumes of hydrogen chloride are given out. So we're going to have a look at another reactions that acyl chlorides can go through. Let's get rid of that. We don't need that. So acyl chlorides and acid anhydrides react in a very, very similar way. So this is what we're going to look at now. So acyl chlorides and acid anhydrides. So they react in a really, really, really similar way. So what is an acid anhydride? Well, an acid anhydride is made from two identical carboxylic acids. So it is basically just, it is two identical carboxylic acids. So if you know the name of a carboxylic acid, they're really, really easy name because we take away the acid and we add anhydride. So for example, if it was, if it contains ethanoic acid inside it, I mean that says ethanic acid, so ethanoic, there we go, acid. If it had two molecules of ethanoic acid inside it, the name of the acid anhydride in this situation, we get rid of the acid and add anhydride. So it would be ethanoic anhydride. And that's for naming it. So what you need to do is you need to know the reactions of water, alcohol, ammonia, and amines with acid anhydrides. But like I've just said, they react in a really, really similar way. They're almost identical. So again, I'll put them four down here. So you need to know their reactions with water, ammonia, alcohol, I've forgotten what that one was then, alcohol and amines. They're almost identical as acyl reactions with the acyl chlorides, but I wrote acid chlorides here, I've just realized I should say acyl chlorides. But they're just less vigorous. So they react exactly the same way as these with the acyl chlorides, but it is just a less vigorous reaction. It's a less vigorous reaction that's going on. And what you get also forming is a carboxylic acid formed instead of your hydrogen chloride. So I'm going to draw you an example. I'm actually going to compare the two, actually. Before I even do that, I'm going to draw you out an acyl chloride. No, I'm not. I'm going to draw you out a carboxylic acid, and I'm going to draw you the ethanoic anhydride just to explain how they look. So when we were naming them, I said basically they're two identical carboxylic acids. So if we had two carboxylic acids, let's have ethanoic acid. Let's use ethanoic acid as our example. So here we go. We've got ethanoic acid here. I'm just going to draw it twice in two different colours just so we can see where the bonds join. So we've got ethanoic acid. For us to make ethanoic anhydride, what happens is we have the bonds form, and what actually happens is we have the loss of these. I've just drawn these the wrong way around. It can go that way around. It doesn't really matter, but just for purpose of what I'm doing, it's easy to have them the other way around. You'll see why in a second, because I just want my oxygens and hydrogens next to each other. So what will happen is these will react together. form water because it is a condensation reaction. And what will happen is this. We will get this forming. We'll get ethanoic anhydride, which will look something like this. We have our CH3 at the end. Our oxygen. And then the oxygen joins to the carbon of the second carboxylic acid. And that here is, this here is our ethanoic anhydride. And then we also have H2O, which came from there. So back to what I was saying, they react in a very, very similar way to acyl chlorides. So when they react with water, alcohol, ammonia and amines, they react in a very, very similar way. The only difference is they're less vigorous and you get a carboxylic acid formed instead of hydrogen chloride. So I'm going to draw you an example out. Let's use that ethanoic anhydride that I've just been talking about a lot. So we've got ethanoic anhydride. And it's going to react with methanol. Here again, just writing it on, we've got ethanoic anhydride reacting with methanol. And what we get formed is methyl ethanoate, the same as we still have a carboxylic acid being formed because it forms exactly the same as it would have done before. Make me mad. Right, here we go. So it forms methyl ethanoate. Also, rather than that hydrogen chloride gas being given off, it produces ethanoic acid. So back to acyl chlorides now. All acyl chloride reactions are nucleophilic addition eliminations. So all those times that I'm saying, yeah, they easily lose their chlorine to make these other molecules. What is happening is that nucleophilic addition eliminations that we've talked about before. So I'm going to draw one of those out now and just talk it through with you. So let's get a nice big space to draw this out and make this sensible. So in acyl chlorides, both the chlorine and the oxygen atoms are going to draw electrons towards themselves. So the carbon is going to have a slightly positive charge. So I'm going to draw an acyl chloride out for you now and explain that. So let's get this a bit bigger. Oops, no, let's start that again. So we've got our acyl chloride here. And like I've just said, the chlorine and the oxygen atoms draw electrons towards themselves. So they have a slightly negative charge here. So they have a slightly negative charge. And because of that, it means that the carbon has a slightly positive charge. Because that carbon has that slightly positive charge, as we've talked about in the past, it's easily attacked by nucleophiles. And so we're going to go through now the mechanism for a nucleophilic addition elimination reaction. And it's going to be between ethanol chloride and methanol. So I've drawn out our ethanol chloride, and now I'm going to draw out methanol. So here is our methanol. And remember to draw on whenever you're drawing out nucleophilic addition eliminations and you draw nucleophiles, you need to make sure you have those lone pairs marked out. So what happens here is methanol is a nucleophile in this situation. So this is our nucleophile. Methanol is acting as our nucleophile. It attacks the partially positive carbon on the acyl chloride. Remember, curly arrows. It's going to come and attack that partially positive carbon on the acyl chloride. And a pair of electrons from that carbon-oxygen double bond are transferred to the oxygen. So remember to draw it from the middle of that bond to the oxygen. And this part is our nucleophilic addition, this first part. Then what happens? Let's have a look at what it should look like now. So this is what we will now have. So if we look at the charges now, our oxygen is slightly negatively charged, is negatively charged and has a lone pair of electrons on it. This oxygen down here has now got a positive charge. So now what happens is the pair of electrons on the oxygen reform the double bond. So this oxygen at the top that was originally from the acyl chloride, this pair of electrons that are up here, this lone pair, are going to now reform that double bond here. And the chlorine is now going to be kicked off. So this bond breaks and the chlorine is kicked off. So this is the elimination part. The next stage of elimination is we will have this. So we've now got our acyl chloride that's bonded to the methanol. It's reformed its oxygen double bond. And it has lost that chlorine. I'm going to draw all the bonds on now because I've just got floating things. So that's a double bond reformed. So the chlorine, well, our oxygen here has still got a positive charge. So the chlorine, which is now floating around, has a negative charge and a lone pair of electrons on it, now is going to come along and bond in the hydroxyl group. So the carbon comes along and bonds in the hydroxyl group. So it comes and bonds here. And then this bond between the hydrogen and the oxygen is going to break because of that. So finally, what happens is we will get this. Is we've now got and our hydrogen chloride's eliminated. So that's eliminated off. And we should now have hydrogen chloride here. That is the whole process of that. So if I break it down and we zoom it out a bit, then I try and get it a bit bigger so we can actually see it. This part here is our nucleophilic addition. So that is our nucleophilic addition section. All of this is our elimination. Again, go through it. Methanol is a nucleophile in this example that we've used, and it's attacking the partially positive carbon on the acyl chloride, and we have that bond breaking between the carbon and double bond oxygen. Then that lone pair of electrons on the oxygen reforms a double bond and kicks the chlorine off. And then here we now have the chlorine bonds with the hydrogen group in the hydroxyl group, in the hydroxyl group, and then the hydrogen chlorides eliminated. That should be a carbon again. It's gone to a O for some reason. So the other reactions of acyl chlorides that you need to know all work in exactly the same way. So we use alcohol as an example, but whether we're reacting with water, ammonia, or primary alcohols. All you would need to do for this mechanism is change the nucleophile to water. So the nucleophile could be, so instead we just would change our nucleophile. So our nucleophile could then become, for example, water. So instead it could be water. And that would have lone pair on here. It could be ammonia. Lone pair is going to be on the nitrogen, or an amine. So an example of an amine, CH3, lone pair on the nitrogen, H2. Last thing I'm going to look at is ethanoic anhydride. So again, anhydrides, acid anhydrides, very similar to acyl chlorides. And we're just going to look at ethanoic anhydride in particular for what it's used for in manufacturing. And it's actually used in manufacturing a drug. So that is ethanoic anhydride. Ethanoic anhydride is actually used in the manufacturing of aspirin. And what we need to know about aspirin is actually an ester. And when we make it, we make aspirin by reacting a molecule called salicylic acid. So we react salicylic, and it's an awful word to try and say, salicylic acid, and we react it with ethanoic anhydride or ethanoyl chloride. So we react it with either ethanoic anhydride, ethanoyl chloride. In industry, ethanoic anhydride is always chosen. The reason it's chosen rather than using ethanol chloride is because ethanoic anhydride is cheaper than ethanol chloride. It is a lot safer to use because it is less corrosive. It reacts more slowly, which makes sense because, like we said, acyl chlorides are almost identical to how acid anhydrides react, but acid anhydrides are less vigorous. And it also doesn't produce those dangerous hydrogen chloride fumes. So there's no HCl fumes being produced in this situation. I'm just going to draw you out the mechanism of salicylic acid being reacted with those. So I'm just going to draw that out really quickly. So I'm going to show you what salicylic acid looks like. So salicylic acid reacts. So this is salicylic acid. It is an ester. I'm awful at drawing them out. Oh, I should have had a point on it. That will work better there. I should have had my dotted paper. And that is going to react with ethanoic anhydride. And remember, ethanoic anhydride is 2 molecules of ethanoic acid joined together. And it bonds together to form aspirin. And this is what aspirin looks like. And the waste product, it also makes, because we said it doesn't make those dangerous hydrochloric acid fumes, it makes another carboxylic acid, which obviously is not dangerous. And we get ethanoic acid being made in this situation as well. So again, we've got our salicylic acid here, our ethanoic anhydride. They're reacted together and they form aspirin and ethanoic acid. So what we're just going to go through now is a couple of exam questions specifically on acyl chlorides. And I'll go through how many marks they are and areas that you might want to point out and pick out when answering these questions. So ethanoyl chloride. So straight away, if you saw a question like this, ethanoyl chloride, well, you know we're looking to acyl chloride, and ethanoic anhydride both react with methanol. So I would pick this up straight away and I go, okay, well, I've got ethanoyl chloride, ethanoic acid anhydride, and they're both reacting with methanol. And I might even make a note above each one just for my own mind, just so I know what's going on. And I might actually just note and say, okay, well, this is an acyl chloride. This is an acid anhydride. And this is an alcohol. You're asked in the first part of this question to write equations for both reactions and name the organic product that is formed in both reactions. So you would get a mark for writing the equation for ethanol chloride reacting with methanol, a mark for showing ethanoic anhydride reacting with methanol, and then the product, the name of the product at the end. So ethanoyl chloride, let's draw this equation out first. So ethanoyl chloride, let's get our pen ready. That's our ethanoyl chloride and we're reacting it with methanol. So let's add our methanol on. And then we're going to draw our products. So our product, I'm going to write the name of the product down straight away because we should know that the product name is going to be methyl ethanoate. So the ethanol chloride, let's draw that out. So we've got methyl ethanoate being drawn out now. And remember, the other product that's formed is that hydrogen chloride fume, so that HCl. So that would be 1 mark for that, 1 mark for naming the product, and then we just need to write the equation now for ethanoic anhydride. So ethanoic anhydride is obviously 2 molecules of ethanoic acid joined together. So that would be CH3CO2 oxygen, reacting it with the methanol, same as the before. Going to make the same product, the same methyl ethanoate, that's not going to change. Shouldn't change. And this side, it's not making that hydrogen chloride. It's going to be making another carboxylic, it's going to make a carboxylic acid. So it will be C3, C plus H. So that would then get you your third mark. So mark for the first reaction equation, mark for the second equation, mark for the name. The second part of this question, so we've got the same top part question. It asks us to give an observation that could be made from a reaction with ethanoyl chloride. So that's really important. Let's pay attention to which one we're asking us to think. Ethanoyl chloride, so that's our acyl chloride. That would not occur with ethanoic anhydride. There's two options. We know that when acyl chlorides react, it's a more vigorous reaction. So you could say, oops, I've moved it along before it needed to be moved along. So we could say in this situation, a vigorous reaction, and that would get you a mark. Or you could say, because it's an observation, so it can't be just saying, oh, a different product's made, because it's an observation is something that we can see, so vigorous reaction. But those hydrogen chloride, the way that's given off is as a gas or as fumes. So that is something that we can observe. So we could say vigorous reaction, or we could say those hydrogen chloride gas fumes are produced. Now, the reason I put the hydrogen chloride in brackets is you wouldn't actually need to say that to get the mark because it's asking for an observation. So just saying that gas or fumes are produced would be enough to get you that 1 mark for this question. So then the final bit for this one, so for question 1, the final part for question 1 is part C. And part C is ethanoic acid can also be used with methanol to prepare the organic product named in part A. And the organic product named in part A was methyl ethanoate. It doesn't give you that in the question. I've just wrote it so we can see it again, just because it isn't going to give it you because that was part of the answer before. And it asks you to give one advantage of using ethanoyl chloride. And if you think back to what I was saying earlier in the session, it's because this is an irreversible reaction. So you could get 1 mark for saying it's an irreversible reaction, which helps because it means that we're not going to go through, we don't have to deal with equilibria and a reversible reaction happening and getting that equilibrial point. Or, as we also said, it is a much faster reaction, which people prefer. It happens quicker. So that is also an advantage of using ethanoyl chloride over ethanoic acid, because it is faster and it is irreversible. So the second question that we're going to look at is this. Ethanoyl chloride and ethylamine react together at room temperature. So we've got an amine, a primary amine, reacting with an acyl chloride. So again, I might go along, highlight them, and I know I've got an acyl chloride here and I've got a primary amine, and they're going to react together at room temperature. It wants us to write an equation for this reaction and name the organic product. So let's go through that now. So the first thing I do is I draw out ethanoyl chloride. Most of the time they're going to use ethanoyl chloride. So as we know by now, ethanoyl chloride looks like this: CH3COCl, and we're going to react it with ethylamine, which is CH3 CH2 NH2 at room temperature. And remember, it makes an N-amide, N-sided amide. So what will be produced is this: CH3 CO NH CH2 CH3, and that hydrogen chloride at the end. Name of the product, name of the organic product that we want, name of this product here, that is N-ethyl amide. 1 mark for this, 1 mark for that. You're then asked to draw a mechanism for this reaction. So it's that all about that nucleophilic reactions that we were talking about a moment ago. So they love to do these questions, and these questions will always get you a lot of marks, which is quite nice. So in this instance, it gets you 4 marks. So it's that nucleophilic addition elimination reaction. So we want to show that nucleophilic addition to start off with. So what we want to do is we want to draw out, what do we want to do? We want to draw out that ethanol chloride to start off with. So let's get that drawn out first. So we've got H3C, carbon, oxygen, chlorine. First thing I do before I'd even look at that ethyl amine is I make sure that I've got my charges drawn on. So you want to make sure you've got that slightly negative charge on your oxygen, and then your slightly positive charge on your carbon. Then draw out your ethyl amine even. So remember, you've got the lone pair on the nitrogen. And then it's time for those curly arrows. So remember, the lone pair from the nitrogen comes along and is attracted to that slightly positive charge on the carbon. So we've got that arrow there. That causes that double bond here to break between the carbon and the oxygen. So again, that arrow needs to be from the middle of that bond breaking. So that is the nucleophilic addition. Now we need the 3 stages of the elimination. So let's just draw that product out. What we've got at this intermediate stage at the moment. Make sure you add on those lone pair of electrons that's now there, and still that negative charge that's going to be on that oxygen. Add on the nitrogen, positive charge, hydrogen, your hydrogen, and then your CH2, CH3. This time, remember that because of that lone pair, we're going to reform that oxygen bond, and then your chlorine's going to be eliminated off here. So we've got that arrow there. Now we've got H3C, C double bond oxygen. Nitrogen's still got a positive charge. The oxygen's lost it. And we've got CH2, CH3. Chlorine's over here now with that lone pair with a negative charge. And our arrows this time, we're going to have chlorine's going to come along and attack at that hydrogen here. And then this bond is going to break here. And then our final step is we will have this oxygen double bonded down to the carbon, H3C, nitrogen, hydrogen, CH2, CH3, and our hydrochloric acid. So that is our session on acyl chlorides. Thank you for watching.